Hi guys, James here, and I wanted to go ahead and move on to the section, one of the last sections in the SI review, which has to do with finding all zeros or roots of these really long polynomials. And in order to do that, we're going to be employing a method called synthetic division. But before we do that, I want you to understand that there are a number of different forms of factoring of which we can employ and will employ. Now, they're in sort of an order from easiest to most difficult, and you kind of want to traverse the order of working with the easiest whenever you can. I'm going to try to remember most of them here for you. One of the easiest to work with is going to be just factoring with a GCF. So I'll go ahead and write that here, GCF, which is a greatest common factor. And the way this works is, well, if you have x squared plus x, well, you can see that you can factor out an x. And what you're left with is, well, x times x plus 1. And that's basically how complicated that gets. It's just pulling something out of a polynomial term. Pretty easy. And one of the other really easy ones is just what we've been calling in classes factoring. Uh, I'll just call it factor. And sometimes it's called magic number game, however you want to deal with it. I've been using it as, well, you have this term such as, we'll say, whoops, we'll say 2x. No, sorry. Don't want to do that. We'll say x squared plus 4x plus 4. And this only works with terms that have a maximum power of 2 for the leading term. And you create this, oops, let me do that a little bit better. Create this box here. And what you do is, well, the coefficients of each of these terms are labeled as ABC. Well, you take A times C and B here, and you find out what two numbers for here and here multiply to get this and add together to get this. So your A times C is going to be 4. 1 times 4. And your C, or your B, is also going to be 4. So what two numbers multiply to get 4 and add to get 4? Well, you got 2, right? So you can then separate this as it's positive 2 and a positive 2. So you would say x plus 2 times x plus 2 is how you would factor with that. Then you have the form of factoring which works with a power of 3. And this is called grouping. Remember, it only works with something to the power of 3. Now, say you have something like, let's say, 3x cubed plus 3x squared plus 2x plus 2. Or hold on, let me think for a second here. There. Sorry, it took me a little bit of... So the way grouping works is you put these brackets around your two sets of terms, and then you find, well, what can I break out of each of these boxes? Well, in the top one, I can break out 3x squared. 3x squared. And what I'm left with is x plus 1. And do the same thing over here. What we can break out of this is a 2, positive 2. And we are left with x plus 1. Well, you see these two terms here are the same. There are not two of these terms. They're actually the same term. And you just take and combine your terms here. So you have 3x squared plus 2 as your first. And as your second is x plus 1. These two terms get added for one of your factors, and the ones in the brackets represent your other factor. And that's how grouping works. It's kind of some magic voodoo, and you shouldn't really question how it works. You could go through the steps and prove it, or find someone else to prove it to you, but just memorize how it works. It's fairly simple once you practice it. One of the other things is difference of squares. And the way this works is, well, if you see something like x squared minus 4 as a factor or a polynomial, well, you should recognize right away, well, this is a square, and this is a square, and this is a different sign. So I remember that phrase as being difference of squares. So what you do is you take the unsquared version, and the way you get a difference of squares, if you've ever done it through foiling, is you FOIL together conjugates. So bring down the conjugates, the square-rooted conjugates. So the conjugates are going to be the square root of x squared, which is x, plus the square root of 4, which is 2, times its conjugate of x minus 2. And that's how you factor a difference of squares. Finally, may have to clear some room here, or come over here, because we'll erase all this anyway. Finally, a way we can factor, and this should probably be a last resort, is going to be the quadratic formula. Now, the reason the quadratic formula should be a last resort is because it's a lot of extra writing, a lot of extra work, a lot of extra time. The advantage of the quadratic formula is that it will give you your factor regardless if it is rational or irrational. It will give you an actual answer. And you're just going to have to kind of remember the formula as being negative b plus or minus b squared. Sorry, it's not a parenthesis there. B squared minus 4 times a times c all over 2a. And the place you get this from is from the standard form of your polynomial, and it only occurs like this: ax squared plus bx plus c. So if you have a formula like that, or you have a polynomial like this, you can use the quadratic formula to find out your factor. But it's really just a last resort and is not really recommended to be used unless you have to. So I'm going to go ahead and erase all this, and we can get started with our factor of our function. So the first thing you should do when you look at a function like this is realize, well, you're already given some information. The first being that this number here gives you both your capital Q, which I'll talk about in just a second, as well as your y-intercept. Y-intercept being negative 18, your capital Q simply being the absolute value of this number, which is 18. You are also given from your first coefficient your capital P, which is 3. And it also kind of helps you determine your end behavior. I'm going to go ahead and put that right now. This whole thing helps give you your end behavior. I'm going to put that over here. End behavior is going to look like your leading term, 3x to the 4th. And if you remember, well, that's a parabola. It's pretty sharp parabola, so it may look something like this. And there's one last really important piece of information that you should automatically notice, and that's the power of your leading term is a 4. What this means is you can have up to 4 roots. And you can use that when you're done to check. Now I'm going to go ahead and get rid of that. And we will go ahead and start working on this. Let me move this up here a little bit out of my way. Okay. Now, the whole point of working with these big problems is that we start to use a new method called synthetic division. And it's a very time-consuming process. There's a lot of writing, a lot of addition, subtraction with it. And so it's kind of a process that we want to use and be done with right away if it is one of our forms of factoring compared to the 5 forms that I just showed you. If you're able to do one of the other forms of factoring, it'll save you a lot of time, with the exception of the quadratic formula, of course. So the first thing we want to do, and for this particular function, we're going to have a given. Given x equals negative 2 is a root. And this will save us a lot of time because we'll have one to work with rather than just going through them all. You'll see why in just a second why that matters. So you take your q here and lowercase q over lowercase p. And what you're going to do with this is create a fraction based on the factors of those numbers. Well, the factors of the uppercase q are going to be 1, 2, 3, 6, 9, and 18, because these are the numbers you can multiply together to get 18. And the same thing for the p. 1 and 3 are the possible numbers we can multiply to get uppercase p. I'm going to move this over. Try to buy myself some space here. Okay. Now you take these numbers and just kind of combine each of them with their possible denominator, each possible numerator with each possible denominator. And what you're left with is 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, 6 over 1, which is 6, 9 over 1, which is 9, 18 over 1, which is 18, and then 1 over 3, which is 1/3, 2 over 3, which is 2/3, 6 over 3, which is just 2, so we don't really have to put that one in. I skipped 1 over 1 as well. 1 over 1 would just be 1. We don't have to put that in because we already have that. Or, oh, no, sorry, I'm getting confused here. 1/3, we did that one. 2/3, that one's here. And 3/3 is going to be 1. So we don't have, yeah, that's where I messed up. 3/3 is just 1. We don't have to put that one in. 6/3 is just going to be 2. We don't have to put that in because it's right here. 9/3 is simply just 3. We don't have to put that in. 18/3 is simply just 6. So we don't have to put that one. We have all of our numbers. And don't forget, these are plus. There's a positive and a negative for each. So instead of having 1, 2, 3, 4, 5, 6, 7, 8 answers, we actually have 16 possibilities. 16 possible roots. 16 possible things we can try for synthetic division. And here's the actual process for synthetic division. Since we are given -2 is a root, let's go ahead and start with that because that'll just get us off to a nice start here. -2, and this is the way you set up your synthetic division. We're going to go ahead and bring down the coefficients of each of these terms up here, starting with the 3, the 5, the 25, the 45, and the -18. And something I want to point out right here is that when you look at a long function like this, in case this term is not here, this 45x, in case this 45x is not here, and you go straight from x to the power of 2 to x to the power of 0, which is what that is -18 times x to the power of 0, your constant term. If you go from 2 to 0, you need to recognize there's something wrong. I was missing an x to the power of 1. Well, what you have to do then is create a term to be able to solve using synthetic division. You need a placeholder term. So you would insert 0x to the power of 1, or just plus 0x. So be aware of that if you run into that. Let's go ahead and take that off now. Okay. So the first thing you do when you're doing synthetic division is you bring down your first number. And then it's kind of this circle where you multiply the number below to your term that you're attempting to divide out of your function, your giant polynomial. 3 times -2 is going to be -6. -6 plus 5 is -1. -1 times -2 is 2. 2 plus 25 is 27. 27 times -2 is going to be -54. -54 plus 45 is going to give you -9. -9 times -2 is going to be +18. +18 plus -18 is just 0. Now you can determine how far your remainder goes in these numbers by the amount of terms that you're attempting over here. Since you're attempting one term, well, then you just come over one spot. That is your remainder. You have a remainder of 0, which means that this number factored out of your polynomial evenly. So what you're left with is that you're able to draw out x equals -2 or x plus 2. If you were to set it to 0, you would find that x equals -2, which is where that number came from. So this is already a factor of your number, your polynomial. What you do now is you bring down the rest of your term. Now, you need to recognize, starting from your remainder, each of these has a power. This is x to the power of 0. This is x to the power of 1, x to the power of 2, x to the power of 3. And if the term continued on, it would be x to the power of 4, and so on and so forth. So that is how you set up your new term. So let's go ahead and bring down our new term. And we're using these numbers here. Don't forget, these are the coefficients of your terms. So we're going to have 3x to the power of 3. Oops, sorry. 3x to the the power of 3 minus x squared plus 27x minus 9. And what we have here is our original. Don't forget that this is all f of x. It's just been it has one factor pulled out of it. So let's continue on. And if you notice, we could continue on trying positive 2, negative 2 again, 1, negative 1, 1/3, 2/3, and all 16, and do this entire synthetic division process for all 15 other term or factor possibilities. But if you take a look at what you've got here, you'll notice that you've got a leading term with a power of 3. And if you remember in our different factoring methods, if you have a leading term with a power of 3, well, then you can attempt to do factor by grouping. So let's go ahead and try to do some factor by grouping. Do not forget your factor that you've already pulled out. We can't lose him. We want to keep that. The next thing we'll do is we will try to factor by grouping. And the way we'll do that is we will write this, we'll rewrite this term here, 3x cubed minus x squared plus 27x minus 9. Whoops. And remember, factor by grouping, we put these brackets in around our two sets of terms and see if there's anything that we can pull out. Well, you can see we can pull out x squared from that term. And from this set of terms over here, we can pull out 9, positive 9. So then what you do is take and add these terms together. This is some sort of voodoo witchcraft, like I said, and it doesn't really have to make sense to you, just as long as you know how to do it. And so you take these two like terms over here as your first factor, and take these two as your second factor, which is going to be, actually I should write these off to the side here. What you're going to end up with if you pull an x squared out of there and a 9 out of there is, well, you end up with 3x minus 1, and what happens if you pull a 9 out? Well, you have 3x minus 1. Look at that, they're the same. They're your like terms. And there's not actually two of them, like I said before. They are the same term. This is how you factor by grouping. So what we're left with is 3x minus 1. So these three are our f of x factored. Now to proceed further and find out what our roots are, well, let's set these all to 0. X plus 2. I'm going to do these in different colors, actually. So we'll do x plus 2, x squared plus 9, and finally 3x minus 1. This is our function factored out. Set it to 0 to find out what our root values are. So the first one, I'll just kind of go through these in all details. Plus 2 equals 0. So x equals negative 2. And I'm going to do this one first because the other one's going to take a little room. 3x minus 1 equals 0. So we have 3x equals 1, x equals 1/3. And this last one, x squared plus 9 equals 0. X squared equals -9. Then you remember how to get rid of a square is you square root it. So the square root of x squared is x equals square root of -9. Well, wait a second. You can't take the square root of a negative number. That doesn't work. Yes, you can. Under certain circumstances, and in calculus, you will. If you recall in algebra, you can take the negative out of a square root as I. And this leaves you with I as the negative out of the square root, and 9 out of the square root is going to be 3. But don't forget that square root 9 is both positive and negative. You have two answers to get a 9 as a square. So you have positive I3. Actually, sorry, I think I wrote this backwards. I will come out, the negative will come out as I, and your 9 will come out as a 3. And you will have positive or negative 3i. Sorry. So x equals positive or negative 3i. So let's go ahead and write all of these together now. X equals -2, positive 3i, negative 3i, and 1/3. Now, you can easily double check this because remember when I said that the power of your leading term up to 4 roots will dictate up to how many roots you can have. So you can only have up to 4 roots. And as you see over here, 1, 2, 3, 4. We have 4 roots. That falls in line. We don't have 5 roots. If we had 5 roots, we'd say, well, we may have done something wrong here. Gotta figure it out. Oops. So you can go ahead and box that as your answer. And I hope this clears up the process of using synthetic division and some tricks you can do to hopefully not spend the rest of your life doing synthetic division. Thank you.